Hey, and welcome again. So far we have completed a simple linear regression where we saw that a dependent variable depends on one independent variable. And so we saw the y as a function of that independent variable. Now we're going to move on to something else where we're going to show that y does not depend only on one independent variable, but on a number of independent variables. And so we can write it like this, y, which is dependent variable, and also we're going to have x, and this is x1, which is independent variable. But also we may have more. Let's say x2 is independent variable. We can go on, and then we can say xn, depending on the number of independent variables that y can depend on. So with this example, let's go to the data that we have. You can see that in this case we have salary, which is our dependent variable, and the salary depends on not only one variable, which is years of previous experience, but also it depends on some other variables, which could include years employed, years of education, gender, department, number supervised, and so on. So you can see that all these are independent variables, and salary is a dependent variable. So what we did before, the example which we had, I think we worked on years of previous experience, and also we looked at years of education. You can practice by yourself to see the relationship between salary and years employed, salary and gender, salary and department, and also salary and a number supervised. You can do the simple linear regression analysis to test all this. But today all we're going to do is to put all of them together, and that's what we call multiple linear regression analysis. And so in this case, we're going to say that y is a function of x1, x2, x3, and then xn, depending on the number of independent variables. But at the same time, we're going to consider, or we will still consider, the error term. I'm going to write something which is not statistical, but at least for us to understand. So I'm going to put etc here, meaning that y is a function of x1, x2, x3 up to xn, but still there are some other factors which are not considered, which may have an effect on y, but they are not considered at that moment. So in this case, you can see that salary depends on these factors, but still there are some other factors which in fact can determine salary for this particular kind of data. And so instead of writing etc, we could write e, which is the error term. So let me write it here. Y is a function of x1, x2, x3, xn, and we'll put the error term there. So let me do some changes here. So now we can write this model, which we developed for a single linear regression model, but now we can write it for the multiple linear regression model. So we can say y y equals to alpha, which is y-intercept, and then we're going to add the slope of x1 times x1. And so let's call this slope for x1 to be beta 1 plus beta 2. We're writing beta 1, beta 2 to differentiate the slope of each variable. And so here we have beta 2 x2 plus beta 3 x3 plus, and then plus beta n x n plus the error term. So that's how we can write our multiple regression analysis model. So in order for us to run regression, then we need to consider the hypothesis, and therefore we're going to use the same hypothesis testing that we considered for the simple linear regression model. And in this case, we're going to test all the slopes. And so in this case, we can say BI, showing that any slope for all these variables, right here a little. And so here also we'll say right here. So we'll say that the slope, or the particular slope of these variables, is not different from 0. That's the null hypothesis, and we have 95% confidence level. And the alternative hypothesis is that the slope of a particular variable is not equal to 0. It is significantly different from 0, and we will prove that by the probability value of that particular variable, or of that particular slope of a variable, and it should be less or equal to the significance level. And in this case, our significance level is 5%. So given this hypothesis, now we can run our regression analysis, and we'll do exactly the same as what we did with the simple linear regression model. And so I'm going to click on the data, and then I will open data analysis, and I'm going to use a regression tool. And in this case, we need to input y range, which is the salary, and also the x range. So in this this time, we're going to highlight all the variables which are independent variables, or the xi's. Remember, we call them xi, x1, x2, and up to xn. But we have to define what is x1. So in this case, if we can follow the sequence, we can say that x1 is the years of previous experience and so forth up to the last one. We will make sure that the labels are checked, and we need to define where our output range should be. So we'll prefer the output range to be here. And so all I have to do is to select this, or to check the box, and select where I would like my output to be. Remember, you can open the new worksheet or the new workbook. It all depends on your choice, but always I like to have my results close to the data so that I can be able to work on the data if necessary, or I can compare the data with the results. You can also get the residuals, but at this time I'm not going to consider this. Remember, you can get anything you want, like you can plot the residuals, you can plot the line fit, standardized residuals, and even normal probability plot. I'm not going to do that at this moment. So all I'm going to do is to click OK. And when you click OK, then you can see that we have our results. And so we have summary output, and regression statistics will give us the multiple R. In this case, we are looking at the correlation between the Y and Y estimate. In fact, I was supposed to do something here. I was supposed to provide the Y estimate because we are now we are estimating this Y, and so it will be, let me copy this so that I can save time. So in this case, Y estimate, Y estimate equals to all the variables that we have. In this case, yeah, I'm going to leave it like that. And so this is how we can estimate our multiple linear regression model. And so in that case, the multiple R, or the correlation between the estimated values, or Y estimate, and Y observed. And so we can see that the model actually fits in because we have a good, we can say strong correlation, which we call multiple R. And so here I'll write, we have strong correlation. Our model has a strong correlation, and also our model could explain about 82%. So 82% of the observed, of Y is explained, and only 20% is unexplained. So you can see that here we are considering this error term, meaning that there is this 20% which is not explained. So that could be explained by variables which we haven't mentioned in this case. Let me put the color so that we can make this visible. So anyways, now when we look at the adjusted R squared, you can see that it's almost same as the R squared with a little adjustments. And this is just almost 0.8. But still at least 80% is, 80, it is a 79% is explained, and only the remaining part is unexplained. So with this, in this case, I would say that our regression or our estimation is good. And then we need to look at the coefficients. Here we have y-intercept, and in our model we have it here, A, and then we have all these other variables. Remember, we gave them x1, let me write here, x1, x2, x3, x4, x5, and x6. So we have 6 variables, and so here we have coefficients where we have y-intercept, but all these are the slopes of all these x1, x2, x3, x4, x5, and x6. So given these values, or the slope or the slopes of each particular variable, then we would like to find out if each particular slope is significant to the income or not. As I said before, we are not looking at the size of the slope, but we are looking at its significance, and the significance of that particular value will be determined by the probability value. So let me highlight that for to make sure that we can explain this fully. And so you can see that we have different values, but the question is, like here we have years of previous experience. Now it is negative. It doesn't make sense that if you have years of experience, then that means your salary will be deducted, but that is the error of calculation. And we can find if there is any problems, like if there is serial correlation, or if there is multiple linearity effect, and we'll discuss about those later, and they are actually in the notes. And so in this case, although we have negative value here, but if you look here with the p-value, you can see that the probability value is 0.62, and that is way greater than the p-value which is required, that it has to be less or equal to 5%. And when we talk about 5%, it is 0.05. Now, in this case, you can see that years of previous experience is not significant. This coefficient, although it is negative, but it doesn't make any sense. It's more or less the same as 0. It is not different from 0. So that is the test of B1X1. Now let's look at the slope of years employed. Is this value significant? Meaning that, is this slope significant to the salary? So we look at the p-value. You can see that we have this exponential factor here, meaning that we have 0.501457, and so that probability value is almost 0. And so if this probability value is 0, then it is less than 0.05, and therefore we can say that this coefficient, or this slope, is significantly different from 0, and so it is significant. Now let's look at the slope for years of education. It is 1631.830834. So is that slope significant? Then we will find it from the probability value. We can see that its probability value also has this exponential factor here, and with 0.5060077, and so it is almost 0. So it is less than 0.05, and so we can say that the slope for the years of education is significant. Let's look at gender. That gives us the slope, which is negative 1654.074595. So what it means is the gender could reduce employee's salary. A certain gender will make an employee to lose a certain amount of salary. But is that true? Well, we can see this amount, which we may think it's a lot, but when we look at the probability value, you can see that that probability value, which is 0.29, is greater than the 5%. That probability value of 0.29 0.29 is greater than 0.05, and because it is greater, then that means that slope is not significantly different from 0, and therefore we can say that gender has nothing to do with somebody's salary. Now let's look at the department. We have this amount, we have that slope for the department, And so the question is that slope significant? Then we have to look at the probability value. Here we have the probability value, which is 0.001. And so this probability value is less than 0.05. And therefore, we can say that, yes, we can reject the null hypothesis. And in that case, we can say that this is strong. Now, finally, let's look at the slope for the number supervised. We have 134.0143504. And so the question is this slope significant? We're going to test it, and we'll look at the p-value. You can see that the p-value here is greater than the 0.05, and therefore this slope is not significant. So let me do something very quickly as a summary which will make us remember. I'm going to copy this hypothesis and paste it here so that we can use it for a summary of what I just said. So very quickly, let's look at the PI, which is years of previous experience, and we can say that this is not significant. So let me make it yellow and put here yellow. Why is it yellow? It is not significant. Why? Because of this probability, which is greater than 5%, and therefore we will say that the slope is not different, is almost the same as no slope. And in that case, we can say, let me write here, 1, salary do not depend on the years of previous experience. Salary do not depend on the years of previous experience, because that slope is not, this slope is not less or equal to 5%. Let's look at the other variable, which is years employed. So what should we say? In this case, you can see that the probability value, which is 0.501457, then that is less or equal to 5%. And therefore, if that is true, then we know that that slope, or this slope, is not equal to 0. It is significantly different from 0. And so it has effect on the salary. And so we can say that salary depends on years employed. And let's go with the third variable, which is years of education. And so, as we have said, this also gives us 0.50060077, and therefore we can say that salary depends on years of education. Let's go with the fourth one. So the fourth one here is gender, and we saw that this probability value is 0.29, and it is greater than 0.05, and therefore we will not be able to reject the null hypothesis. So we can say that this coefficient here, or this slope, is not significantly different from 0. It is more or less the same as 0. So I'm going to put the yellow color to this, and all I'll say is salary do not depend on gender. So gender is not the factor for salaries in this company. So let's go with the fifth one. And the fifth one is the department, meaning that there are a number of departments. And so working in a particular department, will it determine your salary? So in that case, we can see that we have this amount, which is the slope, and we can see that the probability value is less than 5%. And therefore, we'll say that yes, this slope is significant. It is significantly different from 0. And so we're going to accept that salary depends on the department you are in. So there are some differences in salaries if you work in a particular department. And let's look at 6, and that is we are explaining just the results of this regression. For the department, we can use another approach because we look at how many departments are there in our data. And so let me show you something very quickly. So you can see this red thing here. So it tells the number of, it gives you some information about that particular variable. Now let's look at education, not education, let's look at the gender. So we have 0 for female and 1 for male. And also for the department, we have a number of departments. So 1 represents sales, 2 represents purchasing, 3 advertising, and 4 engineering. So actually for the department, these are the code values. They are not numerical values, but they are code values to explain, to define a particular department. And so here we have 4. And if you go here, you will see that 4 is engineering. We have 1, which is sales. And we have 3, which is advertising, and so forth. And here also we have 1 and zeros. And so that means gender, 0 is for female and 1 is for male. And in this case, we are using what we call dummy variable. And so gender is non-numerical, but we're using dummy variable to show that if it's not male, then it is female. And in what actually we did here, we consider male to be 1 because probably the issue could be that we think that being a male, you could be affected in one way or another, or being a female, you could be affected, your salary could be affected in one way or another. And so that's what we did. That's what we did here. We did the analysis here, and we saw that salary do not depend on the gender. Whether you are female or male, the salary is all the same. And also, for the department, we saw that it all depends on which department you are in this case. And we could say so because of this probability value, which is less or equal to 5%. And therefore, the slope for the department, we can say, is significant. So when you change from one department to another, sorry. So when you change from one department to another, your salary will change significantly. That's what it means. Now let's go to X6. And in this case, we're looking at the number supervised. And so the question is this slope significant? Meaning that if you have additional person to supervise, and if this is the amount which will be increased on your salary, is that amount significant? We look at the probability value. We don't look at the values here. So here you can see that the probability value is 0.14, meaning that it is greater than 0.05 significance level. And in that case, we will say that we will not be able to reject the null hypothesis. And therefore, we will say that this slope is not, is equal to 0. It's not different from 0. And therefore, I will highlight this. And so I will say salary do not depend on the number supervised. The number supervised. So that is how we could actually interpret our data by using multiple linear regression. And so in this case, all we're going to do is to write our regression equation to include variables that are only significant. And so in this case, we have y as a function of a plus, now b1 is not considered, so we're going to write b2 x2 plus b3 x3 plus, about b4, b2 and b3, b4 not, and then b5 x5. So here we have y estimate. Y estimate. And so our y estimation, in this case, we're going to replace the coefficients. And so the coefficient here is this y-intercept here. And so it is 19589.47123. That is y-intercept. We're going to replace this b2 here with the coefficient, which is this one here, and it is 621.056578.9 times x2, and then we're going to replace b3, which is the slope for the years of education, and that one is 1631.830834, and finally we're going to replace the b5 here, which is the department, and so we're going to write 2134.289.319. So that is our model, which includes only the significant variables. Sorry about that. Okay. Let me highlight this. So let me enlarge this for us to see it a little bit more. And so in this case, we can actually interpret our results. And all we're going to do is we can interpret one after another. Remember, each variable can act on its own. So a change or anything that happens with the one variable has nothing to do with another variable. For instance, we saw that salary do not depend on the years of previous experience. That has nothing to do with the salary depending on the years employed or years of education, because all these independent variables are independent of each other. That's what we have to consider. And so when we are going to explain our model or our results, all we have to do is we keep other factors constant and explain one after another. So let's start here. We're going to say So assume X2, which is years employed. So we assume that if X2 is 1, if there is a unit change of X2, meaning that if you work for 1 year in this company, how will that affect your salary? Holding other factors constant, holding this X3 and X5 constant. So we will say that your salary or your estimated salary will increase, because here we have plus or positive. So your salary will increase by 621.0565789 dollars. So then if we want to explain X3, which is years of education, and so all we can say is if you obtain a year, 1 year of education, how will that affect your salary? So we can say a year of education, where we will put 1 in X3. So we'll say that a year of education will add to your salary $1,631.830834, and that amount is significant. And in this case, we hold other factors constant, which are X2 and X5. So now, how can we explain the last one, which is department? So we will hold other factors constant, and then we're going to say that we'll look at move from one department to another. Just move, let's say, from the lower department to the higher department according to the levels of the department. As we have seen, we have 1, 2, 3, 4. So moving from one department to another, how will it affect your salary? It will actually affect your salary when we put 1 here in X5 and hold these other factors constant. And so we can say that your salary will increase by $2,134.289319. So that's how we can interpret this. And it is very important to explain one variable after the other, as I have said, because they are independent of each other. And so we have to hold other variables constant and look at the per unit change of that particular variable. And we can see that the dependent variable will change by the slope of that particular variable. But sometimes we may have more information. For instance, let's look at X2, which is years employed. And let's assume, let me write here, assume that X2, which is the years employed, let's say years employed is 2, meaning that a person has been in this company for 2 years. And then we ask how many years of education, which is X3. And so let's say this person has, let's say 2 years, or let's take something else. This person has 3 years of education. And let's consider we have X2, X3. Let's go to X5. So we can say now which department this person is working at this moment. So we can say X5, and this person is working in department number 4, which if I can remember is engineering. So how can we estimate the salary of this particular person who has worked with this company for 2 years and has 3 years of education, and also the person is working on the department number 4? So to answer this question, we will actually improve our equation here. And so we have this salary the first value, which is y-intercept, meaning that, sorry about that, we have this value here, the first value, which is a or y-intercept, meaning that the person has to earn this amount regardless he or she has years of he worked in the company for many years, regardless the level of education and also the department. As long as this person gets into job, that will be the base salary. Now, the salary will increase depending on how many years the person has been in the company. So let me go in here and change X2. We say that this person has been working for 2 years, and all we're going to do here is to put 2, put the bracket, and we are going to put 2 years employed in this company. So how about X3? This person has 3 years of education, so we will change X3 variable to 3 years of education. And how about the department? We are going to change X5, and we can put there 4. And so what we have to do is just the matter of calculations. So all we have to do here is just the matter of calculations, and so we can get the Y estimate. And I'm going to ask you to do that. So do the calculation here. Take this A or Y-intercept plus this value times 2 plus this value times 3 plus this value times 4. So you will get the Y, or we call Y estimate, or we can estimate the salary of this particular person. And for exercise, you can actually go to the data and just take one salary here. Let's say this particular employee, and try to estimate this salary by using calculations which we have made. And so this person has been in this company for 5 years. Has the experience of 5 years before he joined the company, but that has nothing to do with the salary because it is not significant. But now if you go to the years employed, we can see that because years employed will have a significant effect to the salary of this person. So you're going to take that slope of the years employed times 7 plus the slope of years of education times 4, meaning that this person has 4 years of education. And then this person is male, but we are not going to consider gender because gender has nothing to do with the salary. We have proved that. But we have department, and this person is working on the department 4. And so we're going to take the slope of the department times 4. You will do it exactly the same as what we just did here. And then you can actually determine the salary, or you can estimate the salary of each particular person. Now remember, this is just an estimation, and it may overestimate the value or it may underestimate a particular value. And that's why we need to find the residuals, or to see the residuals, to see by how much our estimation deviate from the observed value. But at least we have good estimation. We can say that we have a good estimation of the data, given that we have a good correlation. We have a strong correlation, and also our model could explain about 82% of Y, but we have that 20% which is not explained, and that's why we may overestimate or we may underestimate. And so that's all. If you have any questions, please let me know. But that's what actually we are supposed to do for the multiple linear regression analysis.